All right. Okay, so we saw our axioms yesterday. Just a small improvement. One of you suggested I should replace in axiom 3. I wrote psi of t equals u of t psi of 0 or something like that. I probably had t2 minus t1. And someone suggested that for consistency I should write instead using the notation I was using. It would be something like, psi of t. I mean, this is kind of a trivial difference here, but just to be consistent. In axiom 3. In some sense, these things are mathematically equivalent. Here I'm just kind of using this redundant notation of density operators, which I'll introduce today, which allows us greater generality. So before I turn to density operators, I first wanted to discuss composite systems. And entanglement. Okay, so the standard recipe then is that given a system composed of two subsystems, which we'll call A and B, where A is described by a Hilbert space HA, and B is described by the Hilbert space HB. So I'm not specifying which Hilbert space it is, what the dimension is. Then the state space of the composite system AB is described by Hilbert space HAB equal to HA times HB. We hear this, the symbol, this is a tensor product. In LaTeX, the symbol is O times. Is there anything to know? So this is something that, I guess, at least when I was first introduced to it, it seemed exotic. But it turns out you all already know what it is. So let me first give some examples and then some clarification. So what kinds of situations do we have in mind? So example, A is a spin half particle. Then HA is 2, thank you. Let B be a spin 1 particle. Then HB is C3. Then our joint system, then the joint or composite, here these words mean the same thing in this context. the joint or composite system, if I wanted to talk about both systems at the same time, I ascribe the Hilbert space H equal to C2 times C3, which is equivalent to, well, C1 plus C5, but you're getting ahead of us. C1 plus C4. But yeah, no, it's actually, what I was going for is this. You multiply the exponents, C6.
But one question, within the axioms, shouldn't be another axiom that somehow encodes the fact that you need spin a particle to be fermions and
yeah, maybe.
consider spins to be both.
Maybe. I mean, remember that this idea that we need 3 axioms to use quantum mechanics the way we use it is bogus, right? It's not valid. We actually have a whole bunch of other axioms we need. We need the laws of physics. We need physical insight. We need all this other business to flesh out these axioms and apply them. And so something like that, I think it's a matter of taste if you consider it to be part of these ancillary axioms about, well, the laws of, the forces imply that this property must hold, or properties about identical particles, distinction between fermions and bosons. What I'm trying to say is that the kinematic and dynamical structure of quantum theory is logically independent from those constraints. And so we add those constraints because of other facts we know about the world. And one day I would really like to try to come up with a very clear distinction of how to draw that line, and I don't have that. Asher Perez, who died a few years ago, he was actually one of my quantum heroes. But so he wrote a textbook called Concepts and Methods, something like that. It's a great textbook on quantum mechanics. And he axiomatizes everything he needs in that book with like 20 axioms, and he letters them. So I recommend you have a look at that book because there he spends more time trying to analyze that problem of how am I going to axiomize everything I need to develop the theory of quantum theory and applications. But okay. So anyways, back to our discussion of composite systems. So here we can just multiply these spaces together. Another example is A equals, say, an electron's spin. DOF is degree of freedom. B equals the same electron's spatial degree of freedom. So where is it localized in three-dimensional space? All right. Then we have A gives Hilbert space same as before. I'm just using different words to say the same thing here. And then B is what? Oh, sorry about that. It's a spin half. Thank you. So if I'm describing the spatial degree of freedom, sorry, I probably didn't give you enough information. Let's assume that the electron is a free particle. Then what is the Hilbert space to describe its spatial degree of freedom? Exactly. Here we'll assume it's a free particle. And then HB equals, I don't know if people use this notation, C infinity, but yeah, it's C infinity is, more precisely, we'll say it's L2R. Okay, let me try and stump you guys. So I have a free particle electron with, well, I say I don't care about its spin because I have no equipment that can detect its spin, so I'm not going to worry about it. I have a free particle electron confined in a two-dimensional plane. What's the Hilbert space I need? It's free in the 2 dimensions, but completely constrained in the 3rd dimension. I'm sorry? Yeah. No, well, I'm ignoring the spin. So actually, oh, geez, I should have thought about this beforehand. But now, okay, so another example is, yeah.
Aren't the free particle wave functions not square integrable? So
No. The eigenstates of position and momentum are free particle wave functions that are not in the Hilbert space. But you can have like a Gaussian wave packet.
okay.
So there's lots of states that are valid that describe the possible preparations of your electron. If you want to describe the situation where the electron, you're guaranteed it's at a particular point in space, and you're trying to assign a Dirac delta function to it, then you're getting into this business of rigged Hilbert space. So just to repeat, the question was, aren't the free particle states associated with a definite location not allowed Hilbert space states?
Regarding the spatial degrees of freedom, you talk the particle has some sort of position vector, so can't that be R3?
R3.
Like to specify the position.
Oh, yeah, you know what? That's correct. Sorry, I meant in 1D and I didn't say it, so you're right. Thank you. Thanks for catching that. So here, this is in 3 dimensions, in 3 spatial dimensions. Well, my question about 2D was even harder, given that what I wrote on the board was false, if you assume that was 3D. And then when we describe both systems at the same time, our Hilbert space for A and B, for the composite, for describing both degrees of freedom at the same time, is then, again, HA cross HB, which is C2 cross L2R3. Now notice that the free particle in 3 spatial dimensions, let me just remark that L2R cross L2R cross L2R. So this is the infinite dimensional Hilbert space for my, say, X degree of freedom, my infinite dimensional Hilbert space for my Y degree of freedom, my infinite dimensional Hilbert space for my Z degree of freedom. This is just equivalent to L2R3. Okay, so when you've now, let's make this a little bit more concrete. I don't have to erase, that's right.
But one thing, you're talking about here about composite systems, right?
Yeah.
I mean, the state space or a system. I have 2 systems, right? A and B.
Mm-hmm.
And the Hilbert space of both is the tensor product of the Hilbert space of each, right?
Mm-hmm.
But now you're talking about degrees of freedom.
Yeah.
So,
Well, degrees of freedom are systems. So the idea is that the word system can refer to some degree of freedom. So the point I'm trying to make with these examples is that if you have a single particle and it has 2 different degrees of freedom, it has a spatial degree of freedom and it has a spin degree of freedom, then we need a Hilbert space for each of those things. And the way when we're describing the particle and its spin simultaneously, like the Stern-Gerlach experiment, we needed to account for the spatial degree of freedom and the spin. And what the Stern-Gerlach magnet did is it actually coupled those 2. So what I didn't emphasize in that picture is that when you do a Stern-Gerlach experiment, you send a beam, a single particle with spin through the Stern-Gerlach device. If it's spin up, it goes up. If it's spin down, it goes down. What you've done is you've entangled the spatial degree of freedom and the spin degree of freedom. And the reason you've done that is because you want to measure the spin indirectly by measuring the spatial. So the measurement apparatus essentially correlates those degrees of freedom so that by measuring one, you learn about the other. So that'll become clearer when we talk about measurement. Okay. where's I going next? Right, so you've already seen this. I hope. How many of you have done the harmonic oscillator in at least 2 dimensions in your undergrad? All right, good. So most of you have. So when you did that, you actually were implicitly using the tensor product structure without, often textbooks don't even refer to it, right? So if you have h equals x squared over, how does the harmonic oscillator work? It's px squared over 2m plus kx squared plus py squared over 2m plus ky squared. Then our Hilbert space is equal to L2R cross L2R, 1 for x, 1 for y. So this is the harmonic oscillator in 2D. And then typically the wave function for this system would be expressed in the form, well here, let's just use wave mechanics. The wave function of x comma y can be described, for example, if you start out in a product state, then the wave function will be of the form psi x times psi y. I should call this psi x, psi y. So these are different functions. So, along the x-axis, the particle might be in the second excited energy eigenstate, and along the y-axis, the particle might be in the fourth excited energy eigenstate, or some superposition of the eigenstates of the harmonic oscillator. So these can be independent functions. They can also be entangled functions, especially if you add a coupling term between x and y. But the point I wanted to make here is simpler. I just wanted to say that when you write this out like this, which are actually, this is implicitly using the tensor product. So this is really saying psi x, x, O times psi y, y. So that's a more, so if those of you who saw the two-dimensional harmonic oscillator did not see it expressed this way, but saw it expressed this way, bear in mind that you've already been using the tensor product in that context. Yeah.
So if we do what you just said, if you add a coupling term between x and y, degrees of freedom, then you can still decompose the Hilbert space as a tensor product, right?
The Hilbert space, then it's always true that H is equal to, oh, I wrote it here, yeah. This is always true. Whether the state can be expressed this way, so this statement, in fact, I should emphasize this, so thanks for asking. When I write down the state as a simple product of these two, here I'm assuming that the states are independent, that they're product states. So in fact, let's look at what happens. Let's look at what happens. Suppose I add a coupling term. Suppose I add an interaction term, let's call it, sorry, I should be careful here because, okay, so my H's with this little curly Q are Hilbert spaces, and the non-calligraphic font, which I hope is distinguishable, is a Hamiltonian. So let me just fix my H here. Suppose I add a Hamiltonian term where H, here, let's call this H2D. We'll let H be H2D plus an interaction Hamiltonian where H interaction is equal to A x y. All right. So this is a coupling. This couples the x and y degrees of freedom. Degrees of freedom. Okay. So then generically, generically, after some time t, what you're going to have is some unitary operator given by this Hamiltonian, and your state psi x times psi y is going to evolve in time. This denotes time evolution. So this is under the unitary induced by this Hamiltonian. So here this means this is under u of t equal to x minus I h t over h bar, acting on the state.
Is A time dependent or?
No, A is just a constant. Yeah, let's keep our life simple. So then what I wanted to say is, how are we going to describe the situation of what the state evolves to, right? So let's put a question mark here. And before I can write down a general expression, let's talk about how to compose Hilbert spaces. So let Hilbert space A be spanned by an orthonormal basis. These would be, what are the eigenfunctions of the harmonic oscillator? Right, that's right. Okay, good. That's what I thought. I don't remember the notation for Hermite polynomials, and I've got enough h's floating around. So I'll just write it abstractly as, I'll just call them A sub L, where L goes from 1 to infinity. And similarly, let HB be spanned by an orthonormal basis BK, with K going from 1 to infinity. Then we have the following. Then HAB equal to HA times HB is spanned by the orthonormal basis How trivial is this for you guys? Okay, you can't answer. Someone else. Someone from the back. Do you know what the orthonormal basis is for HA cross HB? Exactly. So it's AL times BK, where L and K are the same indices as before. So it's still countably infinite, but we have a different indexing scheme. That's our new Hilbert space. So what that means is any vector in this vector space, AB, can be expanded as a sum over this basis. Let's start on the left.
Why would you allow to assume to begin with you could write psi x, psi y if you have some coupling term?
Because I was describing an experiment in which psi x and psi y were initially uncoupled. So it's
So then you turn on the interaction at some point and you're like, okay, Hilbert space.
yeah. I mean, I'm just trying to give a simple scenario to illustrate, why we need entanglement and how simple of a model can give us entanglement. We just need 2 degrees of freedom. In fact, the Stern-Gerlach apparatus would have been another way to illustrate this, and maybe we'll do that again later when we talk about measurement. Yeah.
The other thing is, you put the coupling term, right? Let's say I can find a transformation between x and y that takes the whole Hamiltonian and maps it into a free Hamiltonian with, let's say, set P and Q as variables now, right?
We want to map it to a free Hamiltonian.
Let's say I can make a transformation such that that coupling term somehow it's
Oh, right. Oh, like completing the square or
right,
something.
like
Right.
that. So if I try to write my wave functions for the coupling term in terms of x and y, then it will be sums of these products of psi x, psi y, right? But if I do it in the other basis, then I can write it always as a product of 2 functions of, let's say, p and q, and not a sum of them, right?
But implicitly, you still have x and y coupled.
Well, I just chose another letter to write my function.
Oh shoot! Yeah, I
It's
think
like
yeah,
I'm
there's
changing
something
my
here.
basis, right? So
Then
How
you'll have
does
different
cut?
functions.
You'll have a different set
You
of
could
functions.
Yeah.
convert
Right,
it by
right.
you have a-
But the thing I'm going to is that apparently one of the bases, your state is non-separable, but in the other
Yeah,
basis,
okay, all right. I think I know what you're getting at, but let me know if I'm wrong. So basically, here we've chosen a basis for the composite space, which we call this kind of basis. This has a special name. It's called a product basis. You can also have an entangled basis. So the standard example is with two spin-half particles. So if I have, okay, so this is an aside. If I have H equals C2 cross C2, this is, of course, equivalent to C4. And I can choose as a basis, so I can choose orthonormal basis 0, 0, 0, 1, 1, 0, 1, 1. This is exactly like the addition of angular momentum, which I believe you saw last week. Or, okay, so this is called a product basis. Notice that I'm suppressing the tensor product symbol. So what this really means is 0 cross 0, but we save ourselves the trouble of writing the tensor product. Sorry, that's so small. I hope you know what I'm writing here. Does anyone need me to clarify that, or is it clear? So then, or I can choose an entangled basis. I can choose a non-separable. So I'm writing too small. Let me try and improve that. A non-separable basis, orthonormal basis, which would be something like the Bell states. Yeah, so what is it? I guess there's 0, 1, minus 1, 0 over square root of 2. There's 0, 0 plus 1, 1 over square root of 2.
0, 1 plus 1, 0.
There's 0, 1 plus 1, 0 over square root of 2. Oh, what am I missing?
The difference.
0, 0 minus 1, 1? Really? Huh. I should know this by heart. All right. Well, something like that anyways. So yeah, so the point is I can have a basis that's an entangled basis, and there's kind of like no notion of this. No, in fact, this corresponds to the singlet and the triplet. And so here we're taking advantage of the fact that C4 can also be written as, C1 plus C3. So this is the singlet. It's a one-dimensional Hilbert space, so it's spanned by a single state. And this is the triplet. So who wants me to explain what this O plus is? So this, in LaTeX notation, is O plus. And in math notation, it's called a tensor sum. Okay, so a tensor sum is just, if in classical physics, if I have a two-dimensional, if I have a two-dimensional real space, and then I say, and all of a sudden I've lifted some constraint, and my particle can explore the third dimension, Z, say. My particle's this is classical physics. My particle is confined to the xy plane. I lift the constraint so it can explore also the z-axis. Then I would describe my configuration space of that particle is now R3 instead of R2, and in particular, we can just write this as R2 plus R1. Okay, so this is basically adding subspaces of a vector space. So this is one subspace of the vector space. This is another subspace of the vector space, and we're just combining them to get a bigger vector space. So that's what we do here. We have a space that's spanned by the triplet, which is these three states, and then we have a space spanned by the singlet, and we just add them together, and we get a four-dimensional Hilbert space, and this is a basis for a four-dimensional Hilbert space. We can do a change of basis to a product basis, and vice versa. And usually what you do is you work in a basis that reflects the problem you're trying to solve. So if I'm concerned about these particles having separate identities, it's convenient, if I'm going to do measurements on just this particle later on, it's convenient to use a basis which encodes that information. If I'm not concerned about measuring an individual particle, but I'm doing joint measurements on the system, then I'm interested in a basis which is going to reflect that symmetry of what I'm going to do later. So I choose a basis based on the problem I'm trying to solve. So you'll build that experience as you practice working with quantum mechanics.
How do you know that you can decompose C4 into C1 plus C3, why not C2 plus C2?
You can also do that. These are just two choices amongst several.
Okay. But in this case, it turns out to be more convenient to have C1 plus C3.
Well, in this case, yeah, because I'm thinking of the singlet and the triplet, which is a well-known physical situation.
Sorry, how did the spaces correspond to a singlet and triplet?
I was just referring to the lecture you had on
And
total angular momentum.
Zero and total angular momentum.
Right. So you think of C2 as being a spin-half particle, which I didn't mention, so I apologize. Think of this as a spin-half particle. This is another spin-half particle. If I have two spin-half particles, they can be prepared in one of these states, where this state is called the singlet because the total angular momentum number is 0, I believe. And here the total, for these three states, the total angular momentum is 1, and then mj can be -1, 0, and +1, as usual. And here, of course, mj is required to be 0. There's only choice. Call it m0. And here, let's call this m1. So we have four numbers labeling our four states. Four possibilities to label our four states. And here we have four possibilities to label our four. Here we're labeling our states by 0 means spin up on the first particle, spin up on the second particle, spin up on the first particle, spin down on the second particle. So in this indexing, we have s equals a half for each particle, and this state corresponds to ma equals 0, mb equals 0, and so on. And so on for these other cases. Okay, good. So, yeah.
So C4 is the tensor product and the tensor sum of C2 and C2?
Yes.
How are those two different? No, how are O plus and O times different?
Okay, so O plus and O. So O plus, it's just like if 2 plus 2 is 4 and 2 times 2 is 4. So it's a bad example. Okay. Right? So, so you can't really distinguish plus and times. So the point is that, there's a difference between adding spaces. So the meaning of O plus is this. If I have some Hilbert space Cm plus Cn, this is, so for those of you who do lots of formal math, let me just write the answer and then, so you're literally adding the dimensions, right? So here I have m-dimensional and n-dimensional, and I get m plus n. Here, if I do times, then I get a Hilbert space that's the product of those two, which is much bigger. In fact, when we talk about Hilbert space growing very fast, typically when you have, so that's the mathematical difference. Now what's the physical difference? How do you know which physical situation requires use of O plus or O times? So I don't know a general rule, but let me try and illustrate it by examples. Okay, so if I have a spin half particle, and then I have a spin 1 particle, and I'm interacting them, I want to describe the state of the two systems, what Hilbert space do I need?
The cross.
That's exactly right. Right, so it's cross. Now suppose I have a single particle confined to one dimension. It's on a wire, a nanowire. And then all of a sudden, it enters onto a two-dimensional sheet where it can propagate as a current from going from a one-dimensional wire to a two-dimensional sheet. My electron now, I want to describe the wave function. I was describing it as L2R.
Oh, you add that for L2R. You would do the O
Yeah, that's
plus
that's
the other L2R.
no. So that's actually another tensor product situation.
Oh.
What's going on there?
But I mean, when you take, you have the elements of the tensor products, just tensor product of those with the.
Yeah, it's L2R cross L2R. That's weird. Okay, good. Interesting. So the quantum mechanical example is different than the classical example. So yeah, so I was confused because classically I said if you have a vector constrained in, say, one dimension, and then you allow it to explore two dimensions, you would take the sum.
Mm-hmm.
But here, that's where we're describing the position of the particle as a vector. Okay, so now this is a conceptual point which I'll have to tell you guys about 10 times because it's very subtle, but I hope you get it the first time. So, sorry, I'm not being a jerk there. I'm just, it's because I'm worried about this. I'm worried about going here. But okay, so deep fact about quantum mechanics. If you think about quantum states as corresponding, as being analogous to positions of particles classically, then the analogy breaks down very badly. And here's an instance of that. Because if I have a position of a particle in one dimension and then I allow it to explore two dimensions, I'm going to take the tensor sum of those two vector spaces to describe my new state space. If I'm describing a quantum system and I ascribe a quantum state, a preparation is associated with that particle, and it starts in one dimension and then it goes to two dimensions, I'm going to take the tensor product of those two Hilbert spaces. It's going to be L2R cross L2R, not plus L2R. Why does the analogy break down? It's the following. Suppose we go back to the classical example. Suppose I give up on describing the position of the particle by a vector. Instead, I say, oh, I have some probability distribution or probability density in one dimension that describes what I know about the particle. And now I say, oh, now it can access a second dimension. It's now in a two-dimensional situation. Again, I want to describe my information about the particle, which is incomplete. And so I'm going to ascribe a probability density on a two-dimensional surface to be my description of that system. Then what you find is that the probability vector, my probability density lives in a space of functions. What is it, L1 or something like that? L1R? Or the point is that the space of probability densities combines via tensor product, classically. Okay, so this is actually a point I wanted to make, which is I'll make it now. This is quite a digression, so don't get too confused from the flow here. Classically, probabilistic descriptions of particle properties reflect the same mathematical structure structures of quantum states and Hilbert space. Whereas whereas the physical properties in classical physics, the physical properties of classical physics do not reflect the structures of quantum mechanics. do not, I guess I could say mimic. Is mimic CK or just K? The physical properties of cloud do not mimic the mathematical structures of quantum theory. So this is a very deep conceptual point, which is contentious but true. Why it's contentious is beyond me, but people believe what they believe. All right, so okay, so who knows what I'm getting at with this? It's very vague, I know, so but I'll expand on it.
Is this apparently the reason why you have a problem?
Sorry, hold on, wait to the. Yeah.
Is this apparently the reason why people seem to have a problem with quantum mechanics? Because they think it's some sort of classical form of a system where you have incomplete knowledge.
No, so actually it's the contrary. The problem's right. So if you think of quantum states as descriptions of physical properties, like complete descriptions of physical properties, then the mathematical structures of quantum mechanics are obscure and esoteric. If you think about quantum states as physical properties, then you have things like a measurement problem, and there's a long laundry list of problems you come to. If you think of quantum states as being analogous to probabilistic descriptions of the physical properties rather than the physical properties themselves, then there's a beautiful mathematical parallel between classical and quantum physics. You don't have a measurement problem, and there's a long laundry list of benefits. I think that there's a psychological thing going on in the community, or a sociological thing, where quantum mechanics is a fundamental theory, so people want, emotionally, they want the fundamental objects of that theory, the states, to correspond to a physical thing. It's an open question, it's an interpretational question, and certainly you can get insights from both ways of thinking of things, but in my view, you get far better insights from the point of view of probabilistic interpretations. And so let me illustrate that with the tensor product structure in a moment.
I mean, quantum states also do quite a lot of things that classical probability distributions don't do as well.
That's why quantum mechanics is not classical mechanics. But the point is, you can have a short list of things that are similar in quantum and classical physics, or you can have a long list of things that are similar, and then look at what's left over, and then say, okay, well, this here I've captured the essence of what's different about quantum mechanics. So for example, I haven't done this before, so hopefully I get it right.
Because insisting on the latter is sort of giving classical mechanics a more, as in saying that it is more important and more fundamental than quantum mechanics.
Let me.
It's insisting on your own emotional attachment to classical mechanics.
Well, no, you're attached emotionally to the idea that there is something out there. It doesn't have to be a classical thing.
Okay, let me just quell this debate now. This is a debate that should be had only over drinks. So consider again. No, I'm happy to have a discussion, including coffee. Consider again the classical particle. The classical particle. So in 1D, I have a position vector R. Okay. And in 1D, I can also describe the system. So here are possible descriptions. So by the way, this is actually something I plan to talk about today, because I wanted to make the notion of tensor product not exotic. I wanted you to see how natural it is when you think about things probabilistically. So my position vector R, and in 1D I can assign a probability density rho of should I use X or R? Well, I'll call it X. Rho of X here. Well, this is a vector, I guess. Anyways, okay. rho of x. So now rho of x is a function. Okay, so rho of x is a function. And what's the standard notation? I guess there isn't a standard notation, but you want a space of functions that are valid probability distributions. So it's going to be some subset of L1. Okay, so let's.
Would these have to be square integrable as well?
So L1R is the L1R is the set of functions such that the integral over dx of f is finite. Is that right? Yeah? Okay, and so rho of x. Now notice that we put this this modulus here. So when we have a probability density, rho of x, it has the property that it's always non-zero because it's a probability density assignment, and it integrates to 1 by normalization. All right, so that's my probabilistic description of where the particle might be. So to give you a picture, here's my one dimension. I can either describe it via some vector r, which is where the particle is. That's description 1. Or I can assign a probability density and say, okay, well, the particle is somewhere here. So this is my rho of x. All right, so some probability density, which is going to tail off. So here I'm making a definite statement about a property. I'm saying R reflects a physical property of the system. Here I'm making a statement about my knowledge of where the system is. I'm saying, well, it's somewhere in this region. I'm not quite sure where. I think it's more likely to be in this region than the outskirts. Okay? So those are two ways to describe a physical system. One corresponds to complete knowledge. One corresponds to incomplete knowledge. Now let's look what happens in 2D. So in 2D, my new vector R is an element of R2. Here, let's go to 3D, actually. In 3D, R is an element of R3. And so what we're doing here is we're taking essentially R1 plus R1 plus R1. So our spaces, our dimensions, are adding via tensor sum. All right? Whereas if I do the probabilistic description, then I get a phase space density rho of x, y, z. And now this is an element of L1R cross L1R cross L1R. So now when I'm giving a probabilistic description, I'm invoking a way of combining my individual spaces via tensor product. So this is essentially a joint probability distribution of my incomplete knowledge over these 3 degrees of freedom. And what I've done classically is I've taken the, you don't see it this way. I mean, go get a book on probability theory. You won't see them use this notation. It's suppressed. Okay, but when you make it explicit, you see this amazing parallel with quantum mechanics, which it seems like a very, very small minority of people are aware of, which now includes you guys. Did you have a question?
So by doing L1R cross L1, you're basically going, when you say something about its probability, it being somewhere in the probability, related to that, you're saying that it's at some position X and you're supplying information about Y and about Z. But if it could only be in either the X or the Y or the Z, then it would have been L1R, some L1R, some L1R.
If it could only be, I don't know.
If you
I'm
have
having trouble seeing.
restrictions such that it could only be on X or Y or Z, and you could only extract information about one of the 3.
That's a pretty exotic situation. I'm trying to think of what that means.
It was free to be, you weren't necessarily concerned about Y or Z. You could just, at one time you're measuring X, and you leave out the Y and the Z.
I mean, it sounds like you're saying, look, I have my 3-dimensional space, and I'm saying, instead of allowing it to be anywhere in the 3-dimensional space, you want to say it's either constrained to be on this axis, or on this axis, or on this axis.
Yes.
Which I think still, as you're saying, it's somewhere in the 3-dimensional space. You're still stuck with this structure, even though you've imposed. I mean, another way to think about it is you could just say it's somewhere on the surface of a sphere in that three-dimensional space, then it's still an element. It's still an element of this tensor product situation.
So I was trying to draw a very naive analogy to what you're always sort of told in probability. When it's an OR, you add, and when it's an AND, you multiply. So
Right. Right. That's actually interesting, and let me think about it some more, but I'm not sure that that works.
I think what Assad's getting at is he's saying that the space of product states is smaller than the full space.
Yeah, that's certainly true.
That's
Okay, if that's what you're saying, that's fine.
the space of
product states.
is smaller or larger?
The kind of situation you're describing sounds analogous to product states.
What state?
Product states. States with no sum over the basis.
Well, I think in this picture, L1R plus L1R is if you take some function along x and then you just translate it along y along another function. So it's completely separate. So yeah, exactly. That's exactly.
Like if you were saying that you had two lines where your space was like location along one of two lines, then it would be like probability at x on the first line or probability at y on the second line, and then it would be a direct sum. So that would be somewhat similar to having it confined along one of the axes.
Yeah, that's sort of what I was saying.
And yeah, so I think direct sum is OR and tensor product is AND. If you have position along one, anything has a position on one degree of freedom and a position on the other degree of freedom. Yeah.
I.e. the Okay, so I'm being a little bit sloppy here. So I'm being sloppy because I'm making a main point, and I'm being sloppy about a minor point. So the main point is that if we have independent probability densities associated with x, y, and z, then the way we describe the joint probability distribution is a tensor product of the independent probability densities along each degree of freedom. Now, what I'm being sloppy about is saying something has no correlations does not imply independence. So the converse holds. So saying we have independence implies no correlations. So I'm being a little bit sloppy here. Really what I'm saying is if the probability densities are independent, so let's just scratch this, between x, y, and z, then you have the structure. So this is, of course, this is classical physics now. But now you're starting to see how we combine probabilities. And in fact, if you choose a basis of functions, and you want to expand your joint probability density over a basis, then you can take a tensor product basis for each of these spaces and write rho as a linear combination with coefficients over that basis. So all of the things you see in quantum theory that appear to be new are actually reflected in this structure, which is left suppressed normally. Yeah.
There's something that it's unclear for me. It's okay, if it's independent, you can expand it as the tensor product of three different probabilities, right? Distributions. But how can you define a conditional probability in this sense at a quantum level?
On a quantum level.
I mean, if you're basically what you're saying is that we're going to consider, I mean, to each state you associate some probability density, right? That's
You
fine.
reduce yourself to a subspace of this
Okay.
space.
But
Yeah, it's a
in
subspace.
In this case, I can take if x, y, and z are not independent, right? Then I can basically write rho of x, y, z as a sum of rho of x given x, y given y, z times blah blah blah, right? But does that simple thing has a quantum analog?
So yes, it does, and I'm not prepared to go into it, but this is something that.
There's a major problem with that.
Well, so actually, this is something that Matt Leifer and Rob Speckens are working on right now, is developing a notion of conditional states and in the quantum setting. So it's actually an area of active research, how to develop. And I mean, Rob and Matt are both big proponents of this conceptual point of view that, by thinking of quantum mechanics in light of understanding this classical structure, we can actually get much better intuition and understanding about how to describe quantum systems by understanding that it's going to be, so in other words, quantum mechanics is a small correction to this point of view, and it's a very large correction to this point of view. So the kinds of phenomena you would identify as quantum is larger if you're restricted to this paradigm. But if you open your mind to this paradigm, then the number of properties of quantum theory which are different is vastly smaller. And in particular, when you do this, this has a measurement problem. But it's so trivial, we don't call it a measurement problem. And we'll get into that later. OK, so anyways, let me just gather my thoughts here. Right, so here's what happens classically. And then the parallel quantum mechanically may be already implicit in what I wrote. But I mean, so there's an example right there. Instead of L1R, it's L2R. And we're taking the tensor product to achieve the relevant state space. And so here, for example, a wave function psi of x, y, z, if we have independences, if x, y, and z are independent. Okay, I don't know why I'm making my life difficult here. This is like trying to close my garage. All right, that didn't work. So here, so if x, y, and z are independent, then we have product states. For example, psi of x, y, z is equal to psi x of x cross psi y of y cross psi z of z. Okay, so you've already seen the tensor product. You already know what it is. It's exactly the way you combine probabilities. So this, and the reason I went into this digression is because I got tripped up talking about the answer to your question. One of you guys asked the question about, when is it appropriate to use O plus versus O times? And I was talking about a particle being confined to one dimension, and then it's opened up to two dimensions. Well, if we're talking about the position of the particle, we're going to add the spaces. If we're talking about our information or incomplete knowledge of the position of the particle, then we're going to take a tensor product. When the system can explore more dimensions, we take a tensor product of the space of probabilistic descriptions, and we take a tensor sum of the space of physical properties. How many of you are totally comfortable with that point? Okay. I did claim it would take 10 times, remember. It takes a long time. It takes a long time to get comfortable with this. So if you're not comfortable with it yet, don't worry about it. It takes a long time to digest this conceptual distinction. Okay. All right, maybe we should finish with some concrete mathematics to fill out our picture. So let me just run through some of these technicalities. Okay. So we saw how to expand our states over a basis. Oh, just some more terminology. Okay, so if we have C4 equals C2 plus C2. Here, let me do it this way. C3 plus C1. Then let me just teach you some terminology. So we refer to C3 as a subspace of C4. So here, C3 and C1 are subspaces of C4. Whereas if we have C4 decomposed in terms of separate spin-half particles, say, then we refer to C2 is a factor space. Factor space of C4. Okay, so if you talk about a subspace, I'm going to be thinking you have this picture in mind. If you talk about a factor space, people will think you have this picture in mind. So that's the way we use that terminology. And so when we have two factor spaces, we call the system bipartite. If we have three factor spaces, so this would happen if I had, say, 3 spin-half particles. So for example, C8 is equal to C2 cross C2 cross C2. We call the system tripartite.
So where does the term subsystem fit in? Yeah. Should you not use subsystem in the second case?
Yeah, factor space. C2 is a factor space or a subsystem. Well, actually, I think, okay, whereas subspace and factor space are unambiguous, I think subsystem is a little bit ambiguous. So people will use subsystem to talk about a subspace. So it's less clear what people mean when they say it. You have to kind of divine from context what they're trying to say. What else do we need to tell you about this?
Is something like C hat well defined?
No, I don't think so. Not that I know of.
Supposedly C1 is 2 real axes coupled. So if C hat would be taking 1 of these.
I mean, what does it mean to have a vector space that has dimension less than 1? I mean, I'm sure some mathematician has written some paper about this, but I have no idea. You'd have to Google it.
Yeah. So we're going in one direction. As if you have 2 different subsystems, then you construct the Hilbert space of the tensor product of Hilbert spaces, right? That's what we said. Okay. Now, if I have a large system and I want to decompose it in different subsystems, that decomposition is not unique, right? I can make it any way I can.
Can I just use some? Is it okay to use this board so I don't have to erase? All right. Okay, good. So let's look at some formal properties. So if the conceptual pictures here have been troubling, let me just focus on the mathematical properties of the tensor product. Should I write a bit bigger so everyone on this side can see, or I mean move over here? Okay. Properties of tensor product. So here's how you manipulate things. So you have some scalar or complex number. Then you have the following: A tensor B acting on psi tensor phi is equal to alpha A acting on psi cross B acting on phi. And then I can also just put the scalar anywhere I want. I could put the scalar over here. The important thing to realize is that when I have a tensor product of 2 operators, A acts on Hilbert space HA, B acts on Hilbert space HB, then what this means is if I write psi tensor phi, A acts on psi, B acts on phi, and the scalars doesn't really matter, but you can put it wherever you want. it commutes with everything, right? And it's just a multiplicative factor. In fact, it's unphysical anyways. Okay, so you have linearity. So if we have A tensor B plus C tensor D, so notice there's an implicit ordering, okay? So again, my Hilbert space is HA cross HB. So the idea is that when I have the tensor product symbol, it's a place marker. So I write my operators here, and then I write my states here. And now the point is, if you're left of the tensor product symbol, you act on the state that's left of the tensor product symbol. If you're right of it, you act on the state that's right. If you generalize to the tripartite setting, if this is A cross B cross E, then B acts on the second, and the next one would act on the third space, and so on, right? So it's a placeholder, and this is equal to A psi cross B phi plus C psi cross D phi. Okay, then we can evaluate what state we get. And here we've created, assuming A is different from C and B is different from D, here we've created an entangled state, which we'll explore next class. Here's another example. So these are each kind of just examples. Here's another example. If we have alpha psi 1 plus beta psi 2 cross gamma phi 1 plus delta phi 2. Here, of course, alpha, beta, gamma, and delta are all just complex numbers. And then this state is on the left-hand side of the cross symbol, so it belongs to HA. This state is on the right-hand side of the tensor symbol, so it belongs to HB. Then the point is everything's linear, right? So this is all linear. So I'm going to just write this out as alpha psi 1 cross phi 1 plus beta psi 2 cross phi 1 plus, okay, I already made a mistake. What am I missing? I missed my gamma. Gamma. And here, this is gamma. And then I have alpha delta. This is just a regular multiplication.
Shouldn't it be phi 1 cross psi 2?
Did I make a mistake?
No.
Okay. Psi 2 cross phi 2. Sorry, my phis and psis are becoming slightly indistinguishable, which is particularly bad for this example. So the phi, okay, just so you know what I'm talking about, because often people confuse this. So this is phi, and this is psi. Oh, you guys have all LaTeX notation, right? I should be consistent. Oh, sorry. When you erase, you kind of lose your contrast pretty badly. That's pretty sloppy. Okay, you didn't know this would be a LaTeX tutorial as well, did you?
Actually, you need dollar signs to compile it.
Jesus. Okay, I won't write that. That's too bad.
We're already in math mode.
Yeah. All right. Yeah. Yes. All right. So now we have the notion of the dual space. Okay. So I did not tell you about dual spaces. Aggie, is this something I should have covered?
We talked a little bit about it.
Right. So how many of you would not like me to digress and discuss what a dual space is? Almost no one. Wow. Okay. Then I'll tell you about dual spaces. Okay. First, I have to remember what it is. So basically, actually, one of you, well, you probably don't want me to talk about dual spaces. You already told me that that's one of the properties that you need completeness for. Rietz's theorem. Okay. So basically, dual space. So basically, if I have a Hilbert space H, then I can talk about a dual space H dagger. And essentially the idea is that if I have some element, say phi, of my Hilbert space, then I can talk about an element phi of the dual space. Okay, so now what is the dual space? So the dual space is the space of linear functionals acting on the Hilbert space. Okay, so if I have some object f, so a linear functional f is a map from the Hilbert space to the scalars. So what's an example of that? Inner product, right. So take my element of H to be phi. Let phi be the element of H that F is acting on. Then F is going to take phi as input, and it's going to be equal to some complex number C. Okay, where C is an element of the complex field. So now what have you already seen that does that? The inner product. So if I can say, okay, there's some vector F in the dual, well, I can do this. And that's equal to C. Now, one of the beautiful things about Hilbert space, which is not true for arbitrary inner product spaces, is that the space or the set of elements in the dual space itself is isomorphic to the original Hilbert space. That means there's a one-to-one correspondence between every element of the Hilbert space and every element of the dual space. So if you define some functional and you tell me its action on a complete basis for the Hilbert space, so you say, okay, here's F acting on phi 1, here's F acting on phi 2, and so on, and you tell me what complex numbers it gives, I'm going to be able to find a vector in the Hilbert space, which is a ket, and when I turn it into a bra, it acting on that set of states will produce exactly what you want F to produce. Okay, so the dual space, so I think that's Rietz's theorem, right? So Rietz's theorem tells us this. For a Hilbert space, what's the best way to say this? Probably have it in my notes, actually. The dual space to a Hilbert space is isomorphic to the original Hilbert space. To the Hilbert space itself. Okay, so we can think of the linear functionals, which are going to take states and give us scalars. Each one corresponds to some element of the Hilbert space. And that's not true if you don't have a Hilbert space. So completeness buys you the Hilbert space structure, and it buys you this beautiful duality property. And this is what justifies Dirac notation. That's why Dirac notation works. Okay? So this justifies Dirac notation. So I can just talk about the bra and the ket, and I don't have to worry about any other subtleties. Okay, so that is a very okay. So I think you should review this. Every textbook on quantum mechanics that's worth its salt will describe Rietz's theorem as at home. This was a very brief synopsis of the ideas you need to understand because it was kind of off the cuff. But please review this either in the tutorial or on your own time if you're not familiar with Rietz's theorem and the idea of dual space. Okay, right. So now we can return to this list of ways to manipulate vectors. So the point is, if I have some vector alpha psi cross phi, and I want to find the associated dual vector, so I take the dagger to get the adjoint to give me the dual, then what that's equal to is alpha complex conjugated psi cross phi. And then we have the inner product for tensor products. The inner product is the following. If I have a dual vector psi1, phi1, and I take an inner product with some Hilbert space vector psi2, phi2, how do I evaluate this inner product? Everything on the left of the tensor symbol acts on everything on the left, and things on the right act on things on the right. So you just get psi1, psi2 times phi1, phi2. So this is a scalar. Psi1, psi2 is a scalar, complex number. Phi1, phi2 is another scalar, another complex number. And I just get the product of those two complex numbers via this formula. And then just finally, notationally, the following notations are equivalent and hopefully clear from context. So we can write psi tensor phi as psi A times psi B, or we can write it as just, as psi comma phi, where here the ordering, we can suppress the A and B by just keeping track of the ordering of the arguments. And another way to write this is just psi phi. So these are all equivalent ways of taking into account the tensor product. And then the last but not least, I want to talk about representation of the tensor product, but I'm running out of board space, so let me just leave that till next lecture. Okay, thanks for your attention.